Morning, guys. So yesterday we introduced a lawnmower style question. Sometimes it's referred to as a force at an angle kind of problem. We saw we needed to do a little bit of vector stuff, break down any diagonals into the horizontal and the vertical parts. Definitely we had from 2 days ago the friction formula. Basically it's given by mu times Fn. That's a maximum amount of friction against you. If you're not pushing more than friction, friction can just relax a little bit. It just counteracts enough just to bring your net force to zero. The object will only start moving if your Fa is actually larger than friction. Yesterday we also ended off with a fairly challenging question where, because we didn't know what the Fa was, we had the expressions, we had to carry the Fa through the problem, and eventually we came up with an equation that we had one equation with Fa as an unknown, and we can actually solve our way for Fa. So we're going to start off with a similar style question here. I'm going to do this one here as a just a warm-up here. This is called a cart problem. I want you to sort of analyze through the picture. It's sort of like the reverse of a lawnmower style question, but some of the same math that we do here. So let's just have a look here. Do this as practice here. This is our cart problem. We're going to start off with our object. Let's say this object here, much lighter than the lawnmower that we had from earlier, right? So we have 10 kilograms here. This time what I'm going to do here is I'm going to imagine this is like a little cart, maybe it's on wheels, something like that, and I'm actually pulling up along the ankle, and my Fa here, let's give it an Fa here of 80 newtons. I'm going to apply this this force here at 40 degrees, so we have that force there. And I'm going to give you the coefficient of friction here. Let's say the mu value here is a 0.70. Currently we are starting from rest. I want you to do two things for this practice question here. Usually in this question here, in this whole chapter, they're going to ask you to calculate acceleration. I want to know, when you figure out all the tug-of-wars, when you figure out all the sort of unbalanced force, what the net force is, how much is this thing here accelerating? Am I pushing hard enough to actually get this going? If it is going, how quickly is it speeding up? And just to throw in a little bit of that kinematics again here, part B, I want you to determine if it moves, okay? So determine the final velocity after 5 seconds, just randomly make a number, and the distance covered. Now hopefully you're going to recognize here in part B of the question, this looks very similar to our kinematic section. That's totally true. We're going to do our dynamic stuff, our force stuff, to find acceleration. Basically, you have F net is equal to ma, but once you have your acceleration, we're more than welcome to use our kinematic formulas again. Things like v is equal to v naught plus at. We're more than welcome to do all those things again. So you can't quite forget that chapter yet, but again, in this case here, we're looking a little bit more big scale. Well, what were the tug-of-wars that actually caused the acceleration? Newton's second law had said, I need net force to actually have an acceleration. So again, I encourage you just to pause the video, right? You can give it a try, and then when you come back, you can have a look at how you did. What I would do here is I would start off with a Freebody diagram. Again, they didn't ask you to do this, but by drawing a Freebody diagram here, we're actually sort of listing for you which are all the tug-of-wars that we have. I'd always start off with gravity, because as long as there's two masses here, but I'm a 10 kilogram mass here, and I'm on the Earth's surface here, there's definitely going to be an Fg. We are sitting on the surface, so the surface should be supporting me a little bit here. There should be an Fn. Normally, if I wasn't doing anything, the Fn was exactly counteracting gravity. This time, what's happening here is I'm actually applying a force at an angle. Again, angles are always a little bit hard to deal with, so what we're going to do is we're going to break up, well, what's the horizontal part of that force, and what's the vertical part of that force? If you compare it to our lawnmower style question from yesterday, what you'll notice is different. In the lawnmower, even though you're pushing the lawnmower sort of along the handle, the lawnmower actually had a handle that was directing the force down and to the right. This time here, I'm actually lifting it up and to the right. So we're going to see what's going to happen to the Fn in that case there. But there we go, we have Fx, Fy. Just for convention, I'm going to pretend this is trying to be dragged over to the right. We're going to then have a friction force here. Again, if they don't mention any coefficient of friction, you could just assume frictionless. In this case here, because it gave me that 0.7, I'm going to need that number for friction. So, looks like a good diagram to me here. I'm going to take my applied force, so that's the only problematic one here. My applied force here is 80 newtons. I can't deal with that at a diagonal. Let's do our vector work here, and let's figure out how much is it Fx and how much of it is Fy. The Fy is the opposite side of this 40 degrees, so 80 sine of 40, where the other side is going to be 80 cos of 40. Making sure you're in degree mode here. 80 sine 40, this gives me, give or take, about 51 or so. 80 cos 40, this gives me 61. Right? So instead of worrying about having to do 80 at this random angle here, you can think of, oh, that diagonal is pretty much, I'm going to the right just 61, and I'm pulling upwards 51. Normally, if you sort of look at the way we've done these problems here, we've been studying the y direction first. In the y direction, we actually have three forces. We have a gravity force, Fg. I always start with Fg because we have a formula for it. It's m times g. M is equal to 10 kilograms. Let's multiply it by 9.8. So that gives you here 98 newtons. So that's how hard gravity is pulling down on it. Normally, I would say Fn, oh, it just counteracts gravity. It's the opposite direction. The ground needs to support it so that this cart here doesn't fall through the ground. That would typically be true, but in this cart problem, you'll realize, just like a lawnmower style question, as I apply a force along a diagonal, I'm actually supplying an extra upwards force of 51 newtons. So there is an Fy that's also pulling vertically. Fy is actually a 51. So my question for you here is, we had calculated Fg is 98. We're pulling upwards here 51. First thing is, am I pulling hard enough to lift the object off the ground? Well, no. I need to pull at least 98 to counteract gravity here. Gravity is still winning out here. But what's going to happen here, this is like that bird coming up behind your shoulders here. It's trying to lift you up, can't quite lift you off the ground, but it will support some of that mass. The Fn says thanks, right? The Fn used to go 98, but because I'm also supplying a 51, if the Fn pulled the whole 98, then in total, this object here would lift off the ground, which doesn't happen. The Fn relaxes a little bit and it says, all right, so between us two forces, it's going to be Fn and Fy this time. We are the upwards pulling forces. Fg is the downwards pulling force here. How much does Fn still have to supply when you factor in sort of the Fy, the vertical amount of your applied force, in order to counteract gravity here? The Fn actually realizes, Fn, I only need to support you 98 minus 51, so this is going to be 47 newtons. Again, we can sort of backtrack there. We can say, okay, if the Fn itself is 47, along with the Fy, it's going to amount to 98. Because it's 98 against 98, this object here will neither fly off the ground. I'm not pulling hard enough to lift it off the ground. Maybe I'll make a note of that there. Not big enough to lift like completely off the ground. But definitely I am supporting some of that mass there so that the ground doesn't need to push as hard. The ground actually pulls a little bit lighter. You will feel lighter because someone is lifting you from behind. Now, once we have this Fn here, then we're ready to study the x direction. For the x direction, sure, we still have the horizontal part of my applied force. So I have my Fx. We had calculated that already here. The Fx is actually equal to 61 newtons. So 61 newtons. We still need to figure out, well, based on the grooves and based on how interlocked these are, how much does friction max out? If I pull harder than friction, I can get this going. If not, friction just cancels out all my motion. So for the friction force here, we also have the formula. Friction is equal to mu Fn. The mu value I gave you was 0.70. Really rough surface here. 0.70. You'll notice I'm multiplying the apparent weight. That's why we found Fn first, which is 47. 47 multiplied by 0.7 gives me here 32.9, give or take 33 or so. So that's saying there's enough roughness between the surfaces to go 33 against you. Who's pulling harder? Well, in this case here, I see that I'm pulling harder. Even though I had pulled it up diagonally 80, it's only 61 that's left over in the horizontal. Because 61 is bigger than 33, I go bigger number minus smaller number. The net force, the win, the unbalanced bit, is going to be 61 minus 33. So that's going to be 28 newtons. That's called the net force. Remember, net force by itself is not a force. Net force is just the name I give it. This is what's left over. This is what's unbalanced at the end of the day. If you want to show this in formulas here, you go F net, right? It's the leftover of the tug-of-war. This time it's a tug-of-war between the horizontal part of the applied force minus the friction. I can go Fx minus friction. I usually go bigger minus smaller, just so that we can keep positive. And then we knew from Newton's second law, F net is equal to m times a. Now I had already done this sort of with this tug-of-war analogy here. We have 61. We're minusing off the friction going against you, maxing out at 33, the total mass of this object here, I believe, was 10 kilograms. 10 kilogram mass, and this will actually give you the ability to find acceleration. So we had calculated, we have an overall unbalanced force of 28. That's equal to 10 times A, and therefore the A is going to be 2.8 meter per second squared. Because there is a net force, the net force is not zero, Newton's second law says there will be an acceleration, we've actually been able to find out how much that acceleration is. At this point here, it just boils down to a kinematics problem. We started off knowing that this was at rest. This is at 0 seconds. We know it's going to start accelerating along at 2.8. I want to know at 5 seconds time, how much ground does it cover? And I want to know what's the V final here. So let's just do that here. V is equal to V naught plus AT. Initially here, I start off at 0. My acceleration rate is 2.8. My time, I just randomly gave you 5 seconds of time here. So therefore, the final velocity is 2.8 times it by 5, 14 meter per second. What about the displacement? Displacement, you can do the V squared formula. Just in case I got this one wrong, let's use the other formula. D is equal to V naught T plus 1/2 AT squared. Again, we have a notion of acceleration, so I can't just use the basic motion equation. Nicely here, we're at rest, so 0 times 5 plus 1/2. Acceleration is 2.8 times it by 5 squared. This first term here drops out. 0.5 times 2.8 times it by 5 squared gives you your displacement of 35 meters. From when I started the clock to ended the clock here, we have traveled 35 meters. So you see we can do all that kinematic stuff again. All right? So I know I haven't given you that car problem before, but you see by doing a Freebody diagram here, we list all the arrows, and if you know the arrows, you can actually sort of dissect your way through the problem. Today I'm going to introduce to you one other way this sort of two-dimensional problem is set up here, and we're actually going to analyze this in terms of a gravity on slope problem. Gravity on slope. And the difference here is we sort of know how to deal with two-dimensional problems, right? Anytime there's a vector, I break it up so I can deal with just y's and just x's. But so far up to this point here, the ground has still been flat across. What if we're actually ramped up on a surface? If the surface itself is actually diagonal, then we're going to have to see which forces are actually still diagonal, which forces I need to break up. So for a gravity on slope problem, let me just introduce it to you here. So instead of the ground being a flat plane like this, we're going to imagine ramping it up at an angle. This angle here is going to be at an angle theta. I'm going to solve that through a little bit later on. I'm going to put my mass on this ramp here. I'm just going to call it a mass of m right now. And then let's say this mass here is currently at rest. Can you start off with a free body diagram for this picture? What are the forces that act on this picture here? Alright, so we're going to squeeze ourselves into a center of mass, right? A tiny singular point here that now we know don't have any size or shape. Does gravity still act on this mass? Well, sure. Gravity doesn't care that you're on a ramp or on a flat surface here, and in fact, this is a nice hint for yourself. Gravity always pulls straight down. So I'm just going to do one arrow here, and I'm just going to go, this is gravity, it pulls straight down. Regardless whether we were on a ramp or not, right? Because it always pulls towards the center of the earth. The normal force is a little more interesting in this case here. Normal force, remember, meant perpendicular to the surface. This time, because the surface itself is actually diagonal, the normal force is actually pointing perpendicular to the surface, is actually up in that direction. And what you'll notice here is, wait, the Fn is actually not exactly against gravity. Gravity was a literal straight down, whereas Fn is sort of off at the diagonal. Alright? So that's the normal force. That's one sort of detail we're going to deal with. The other thing here is I'm told that this situation is at rest, or this is a static picture. I just set this mass up. Basically, there's a force that's actually keeping this mass here on the surface. Hopefully you can say it to me here. Well, gravity is going to slide things downwards. If the motion is actually downwards, the only force that we've seen that opposes motion is actually friction. As it slides downwards, the friction force so far is actually going to be upwards. Just a quick caution on that friction force here. It really depends on what the mass is doing. Right now, I'm saying the mass is at rest. The only thing it can do is it can slide downwards. That's why friction is upwards. Later on, I'm going to leave you with a question. What if I send the mass going upwards? What if I slide the mass upwards? If I slide the mass going upwards, then friction opposes motion. Friction can actually go downwards. Friction just goes opposite motion. All right? So those are the only arrows I need. It may feel like, no, it looks like there should be more forces. No, usually in a Freebody diagram, people tend to do too many forces. But in this case here, those are the only three forces. in this case here, when I look at my coordinate system, I sort of end up with an issue because in my regular XY coordinate system, right, my normal horizontal, my normal vertical, my FG is no problem. My FG is going to be straight down. That's just perfectly Y. But I'm going to need to, hypothetically, I need to break down the FN into two parts, and I need to break down the FF into two parts because both of those are not purely horizontal, purely vertical. The reason I'm not going to do that, however, is that's a little bit misleading. Because even if I were to able to calculate the fx and the fy and whatnot, eventually this mass here, the only options it has is either slides down with the ramp or goes up with the ramp here. You'll notice intrinsically here, this sort of becomes a new sideways for this problem. Instead of the real left and right that we're used to here, I want to just actually redefine sideways. What's really nice about all these physical formulas that we've been dealing with, we call this a reference frame. In this reference frame here, where we're in a regular, this is straight flat and this is straight up and down here. Our physical laws, Newton's second law, all that works in our straight system here. If I slightly rotate my coordinate system, let's imagine twisting this coordinate system so that my new horizontal is actually up and down the ramp. This one here, I'm going to call it x prime, and we're going to have y prime. Even though we're in a slightly different coordinate system, this way here is sort of advantageous. First thing, it indicates to me the mass of the object might just slide up or down the ramp, right? It's not necessarily going into the ramp or out of the ramp or up like this. But in a slightly twisted coordinate system, what's happened here is by doing that, the FF is now perfectly in the x prime direction, right? That's sort of no longer diagonal. The FN, which is perpendicular to it, y is always perpendicular to x, so y prime is perpendicular to x prime. My FN is actually also along this new rotated coordinate system. So rotate coordinate system, also called a rotated reference frame here. And in that case there, in our new coordinate system, out of the three arrows, the three forces that I actually had, in my new system, my FN and my FF are already along the axes, so those are not needing to be broken up. In fact, the one that needs to be broken up is actually the gravity that I had right from the beginning. For the gravity here, it used to be phi in my regular coordinate system, but if I now have an arrow that is actually pulling downwards, this is sort of a diagonal relative to my new coordinate system. I need to find out how much of it is in the y prime direction, how much of it is in the x prime direction. Right? So out of the three arrows, by actually rotating my coordinate system, I actually put two of them in my new system, and my FG, which used to be fine, is actually my new diagonal. So be careful how you deal with this triangle here. Here's what we're going to do. I'm going to point an arrow that is perpendicular to the surface. This FG, part of it actually pulls into the slope. I'm going to call it Fin. So that's the part that Fn is actually going to try to cancel out. The remaining part of gravity actually goes down the slope. The down the slope part here should actually be sort of parallel to the ramp itself. So if I can actually scale it out a little bit better for you here. We're looking at components. We're looking at components that do something like this. So F down, parallel to the slope here, maybe something like that. This one here would be parallel. And in that case there, that's the part that's responsible for sliding the object down the ramp. So we're going to call this F down. Right? So I'm going to give you a little bit of just trigonometry work here. If I know the angle of the ramp, right? So sometimes it's 20 degrees, 30 degrees, 40 degrees. That's going to tell you how much I need to rotate it for that particular question. I want to somehow take this angle and match it up with one of these angles here in the triangle. Now, first thing here is in my new x prime and y prime, we know that those are off by 90 degrees. So there's our right triangle again. We're going to start off. You only need to do this trigonometry once. Just want to prove this to you here. For trigonometry here, we're going to start off just with this first triangle, right? Just the triangle that the ramp makes. What I have here is we have the angles. The angles are theta so far. We're going to add, this is a 90 degree, so plus a right angle, plus, I'm going to call this angle here x, just for kicks here. Okay. And we know that the angles on a triangle, they have to add up to 180 degrees. Right? So if I knew what theta was, the x here is complementary. Next thing I want to do is I want to look at just this line here. Right? So no longer the triangle, just this line here. Because this is a line, how much do the angles on a line have to add up to? Hopefully you're able to see to me here. For the line, it also has to add up to 180. So 180 for the line is also made up in this case here, in my new coordinate system, this one here is a right angle. So that one there is going to be 90 degrees. The x there is exactly the same angle we had labeled for the first triangle. So there's still an x. So therefore, what that tells me here is for my triangle that I'm drawing here, the theta of the ramp is actually always going to be this theta, this angle made by f in and f down. So in that case there, the f in is actually the adjacent side. The f down is actually the opposite side. We can break that down. So f in is going to be whatever fg is, cos theta, and the f down is going to be whatever fg is, sine of theta. And in this case here, because the geometry always works out that way here, it's always going to be true. The f in is always going to be the cos, and the down is always going to be the sine. So back when we were doing our kinematics and we were saying, oh, you can't memorize cos is x and sine is y. In this case here, you can, because the theta always ends up at this inward angle. Most common problem I see people do here, they remember FG has to be broken down into components, but they end up drawing a slightly strange triangle. They end up doing something like, we have, so FG goes downwards, and they end up drawing something like, oh, like this, and then it starts looking a little bit weird because that's not quite a right angle. To sort of give you a hint and sort of try to eliminate this problem here, just remember that the Fn, which is perpendicular to the surface, has to be perpendicular to this ramp here. That means that the Fin part of gravity goes opposite that, so it goes into the physically into the ramp itself. The other axis here has to be essentially parallel to the slide here, and in this case here, it's actually going to slide down this way. So that way, if you can make this look nicer at a right angle, you can probably label the F in and the F down a little bit easier. Sometimes physicists like calling the F in the squeeze. It's squeezing the object here onto the ramp. The F down is a slide because that's potentially the part that can actually cause it to actually fall downwards. So let's just work our way through one of these problems here. Just putting some numbers. Let's start off with a 100 kilogram object. Let's say we're up on a 60-degree ramp. The mu, if they don't give you mu, again, you can assume frictionless, but the mu this time is 0.40. Right? Again, they don't differentiate between static or coefficient, but there's enough grooves between these surfaces here to be rough to a 0.4. I'm going to tell you that this object here is currently at rest. What we want to do, again, is I want to calculate the acceleration. Right? Because once I know the acceleration, I can do all my kinematics again. So let's just work through some of the number crunching here. Draw a free body diagram at the beginning. So gravity doesn't care. Gravity just pulls straight down. This is actually the hypotenuse. This is actually the one that I need to break down into x and y components later on. This Fg can be broken down into one part that's F in. F in is going to be perpendicular to the ramp itself. The other part is actually F down. So when we think about, well, putting an object here on a ramp, how come this object here slides downwards? It's actually because of the downward part of gravity. This part here is a right angle. Because we are on a ramp that's sort of slanted here, the Fin goes into the ramp here. We actually have a Fn that points perpendicular to it, perpendicular to the surface. You'll notice the Fn doesn't counteract all of gravity anymore. Fn only counteracts the Fin part. And then later on, in this case here, again, assuming we're currently at rest here, this object here can only slide downwards because of F down. And if this slides downwards, that would mean then my friction force is actually opposing motion. Friction is going to try to keep it from moving. If you start off here, imagine that we start off just on the ground here at 0 degrees. If you steadily increase this ramp, let's say 10 degrees, 20 degrees, 30 degrees or so, in this case here, basically the friction force usually is enough to stop this thing from sliding. But we're going to hit a point here where sort of, oh, no, now it's too steep here. There's not enough friction force here. The F down actually wins over friction and actually ends up sliding this downwards. So let's just try it out here. Again, we typically do this in order. Let's start off with just plain old Fg. Fg is equal to m times g, so it's going to be 100 times 9.8. Regardless if we're on a ramp or not, this one here is 9800, so that's going to be newtons there. This time gravity was the problem. Gravity was the diagonal, so we had said 60 degrees actually amounts to this 60 degrees inside, so let's just calculate what's the inward part for gravity. Fn is actually going to be 980. It's going to be cosine of 60. The F down is going to be 980 sine of 60. So let's just crunch our way through. 980, make sure you're in degree mode again. This one here is 490. The 980 sine of 60, this one gives you 849 newtons. Right, so that's F in and F down. the Fn, which is in the new y prime direction. The y prime direction is essentially, I'm on a ramp like this. The Fn is perpendicular to the surface. It's fighting directly head-to-head against the Fin, that's squeezing it onto the surface here, because again, I sort of know the answer, because the object is just sitting there. It's neither popping off the ramp, nor is it sinking into the ramp. That means these two have to cancel out. So once you figure out what Fin is, I actually know the Fn. The Fn is actually also going to be 490, because it was 490 into the ramp, 490 going off would actually cancel out as well. And what you'll see here is that 490 is not canceling all of 980, because the other part of gravity is going to be canceled out by friction. Or maybe. Well, we'll take a look at that. So, why do we find the Fn here? Again, there's a situation where the Fn is not quite the same as just gravity. Then in the new x prime direction, x prime is sort of sliding up and down the ramp here. We have the downwards part of gravity, Fd. Fd is trying to slide this object here downwards, and the Ff is actually going upwards. And again, depending on which is larger, if this thing here just stays at rest, I know these two have to equal. Well, we'll see based on our numbers if there's an overall win. So let's say this time here, the F net, it's a tug of war. We're going to be fighting F down against friction. These guys pull opposite ways. F down is sliding off the ramp. The Ff is trying to point upwards here. In this case here, my F down, we had calculated was 849. That's the size of that one. The friction force here we have yet to calculate. So Ff is supposed to be mu Fn. That's the maximum we have against you here. Mu is 0.40. What is 0.40 multiplied by the normal force of 490? 490 times 0.4 gives me here 196. Right? So even if you just look at those numbers, you can see, oh, I know what's going to happen, right? 849 is actually going downwards. That's way more than friction even when it maxes out. I'm going to add a net force sliding downwards of about 600, maybe 700 or so. And how we're doing that mathematically is F down minus friction, bigger minus smaller. So we're going to go, the F down is 849. I'm going to minus off the friction force, which happens to be a 196. This is going to be an overall unbalanced force. 849 minus 196 is 653. And then we're going to set this equals to m times a. The mass, right, so Newton's second law, we got to do this second step here. The F net is also equal to m times a, Newton's second law. The mass is 100 kilograms. So 653 is equal to 100 times the acceleration, and therefore the acceleration is 6.53 meter per second squared. Right. And again, we've been able to find the acceleration here. We're ready to do our kinematics again. Right. So let me just sketch out another problem just for you to try out here. There's a slight twist to this problem. We'll see if you can catch it. So, new problem. This time, I'm going to have an object. Let's say this object here is 15 kilograms. It's starting out at the bottom of the ramp. The ramp here is actually 50 degrees. And what I do is I actually give this an initial velocity of 20. So I have a v initial of 20 meter per second. Now, for sure, to actually get this object up to this speed here, I had to have been pushing it along. But you notice here, I'm not, basically, my hand is maybe somewhere down here. My hand is no longer touching this mass here. So I can't influence this object. This object, yes, it happens to be moving upwards, but there is actually no more applied force. It's actually just this starting velocity that's actually trying to get it to climb up the ramp here. I start sliding this object upwards. We know what goes up has to slow down and has to eventually come down. It's going to eventually hit some peak height, just like we did in our kinematics. The peak height is supposed to be 0, right? It's supposed to be at rest at the top. What I want to know in this question here, so giving you some more numbers, I have a 15 kilogram. I'm going to say that the roughness all along this ramp here, the mu is actually 0.60. I'm going to just describe this for you in words here. An object slides upwards at 20 meter per second. So at first I had given it the speed of 20 meter per second. I want you to calculate the distance covered before stopping. And just let me hint at how we're going to do this here. You're going to do things basically the same. So we have our 15 kilogram object. You're going to do essentially the same. Well, we have an FG, that's straight downwards. We need to break up our components, right? Part of it is F in, part of it is F down. That part all is still normal. The Fn, which is perpendicular to the surface, is going to counteract F in. That's what we had said from earlier. But be really careful this time. First thing, there is no applied force. I may have had to push it early on, but you notice that my hand is gone. I don't actually see my hand anymore. So it's just this object happened to leave with the speed here. No one is constantly pushing upwards. That's one of the reasons why friction has its way to actually slow it down. So notice that there is no applied force, even though velocity is upwards. Remember, we don't need a force for motion. But what's going to happen here is because motion is actually upwards, this thing here is actually sliding upwards. If friction were to oppose that, friction would actually need to be downwards. So in this case here, if you were finally later on looking at an expression for F net, you're going to have something like the F in and the Fn have to cancel out. That guarantees that I can stay on the surface here. In terms of the F net, there's actually only two forces that act on it. The downward part of gravity is trying to keep it from going upwards, and this time the downward is actually helped by friction. You might look at the earlier question and you say, wait a second, I thought it was F down minus friction. Well, in the earlier problem it was. This object here is trying to slide downwards. Opposing motion means up the ramp. These two are opposites. This time it's because I gave it an initial velocity going upwards. This time FF is also trying to slow down motion. Because these two both point down the ramp, this time it's actually a plus. So that's how I wanted to just show you here. You're not going to get all these like formulas on a formula sheet here because it really depends on the scenario. Looking at the free body diagram, you should be able to figure out which teams there are. Oh, both of these ones here are trying to pull it down the ramp. And if they help each other, you're going to put plus. If they go opposite direction, you're going to put a minus. So see how you do with that question there, and you should be able to calculate based on the net force. You're going to find acceleration, and then you can do some kinematics to figure out how much ground is covered. I'm going to cover some positive amount of distance before coming to a rest, where at the peak I'm actually at 0. All right? If you have any problems, just let me know. Thanks, guys.